Hello everyone, welcome back to Dynamic Modeler of Cities and Buildings. My name is Josh, and today I'll be covering about sun analysis in using Ladybug tools in Rhino Grasshopper. So what you want to do is you go to Food for Rhino and download Ladybug. So it's this one here. So Ladybug is part of a series of environmental analysis in Grasshopper. So it has other part it has a partners plugins such as Honeybee, Dragonfly, and Butterfly. So Butterfly is for fluid dynamics, for example, like wind and air. Dragonfly is more like an energy analysis, and Honeybee is more like sunlight access in the interior, more like the interior analysis. But Ladybug here is more towards sun and radiation, general sunlight. So what you want to do is to download this from this one here, so the latest one, but make sure that you are logged in. I'm going to skip the installation process because I've already covered that in the ALK video. But what you want to do if you want to have a sun analysis, like for example shadow studies, you want to go to the Ladybug website, which is over here right there. So just go to Ladybug website and Google it. It's this is the address. So this is the home page that you will see once you get in. You want to go to tools, and you want to go Ladybug. So as you can see here, there are a series of tools, like for example Honeybee, Butterfly, and Dragonfly. Also here, it shows how the dynamics between the four plugins in use how to use these plugins, and how does it what kind of potential that it can be. So for example here, Ladybug is to analyze sun data and geometry, whereas Honeybee here is more like radiance and access to daylight. Dragonfly is more energy analysis, and Butterfly here is for airflow and wind. So what you want to do is just to go to Ladybug here, and in here they already provided Grasshopper scripts and components already set up just for a certain exercise. For example, if you want to have a few studies, it's already provided. But what you want right now is to have a shadow studies for analysis. So click that; it'll directly jump straight to here. So there are also examples that you can download for free. So you want to have this one here, shadow range analysis, and just click download. Now I've already installed mine. So what you want to do is just to open this and extract. I'm just going to do this in my desktop, in my documents actually. My documents, click and then go to your documents. Open your Grasshopper, go to your documents, and then just drag across. You can actually open it from there. So it's basically a file. It's already pre-made by someone by the developer. So these are already working. So what you want to do is just to toggle this button here, and then the sun analysis will be ready. So a little bit of settings that I want to show you here is the first one is this one here. So what you need is two things. The first is the base plate. It's the base plate over here, which means that that's sort of like the ground floor where the shadow is casted. And the second solids that you want to have is the buildings that going to have the shadow casted. So it goes to here. So geometry means that it's the ground floor. It's a base shape, and context is the one that creates the shadow. For example, here is the buildings. So, and also you want to have a look at this one here. So that's sort of like setting the hour, day, and month. And timestamp, it means that how many steps, like for example how many sun position that you want to have in an hour. For example, if you would take 6, it's going to take the sun analysis every 10 minutes. And also here, that's a sun diagram that I will show you how it looks like. So if you want to have, for example, the area over here, so that's the center point. So this is the sun path. I need to preview this one first. There you go, it's too big. Yeah, so just delete that. Click that off. And there you go, that's a sun path. So as you can see here, these are the position of the sun, depending on the EPW file that you downloaded. So this is located in San Francisco. So if it's in Melbourne, for example, this is going to the sun chart will be at the north because Melbourne is in the southern hemisphere. But when this is in America, that's why the sun is in the southern hemisphere. So what is set over here is the winter solstice in America, in the US, especially specifically in San Francisco. So if you, for example, if you want to have, I can show you what the time step and how these will affect this one here. So as I mentioned, time step is just like how many sun position that you want in an hour for the sun. For example, if you set this to 6, it will calculate every 6 minutes. So I can just show you. So that's between that's 1 hour, and then if you put the timestamp in, you will see that there will be an additional 4. So it's calculating every 10 minutes. This will create more this will be very useful in if you want to use Sun Subtracto, because it's going to create a more accurate solids and accurate Boolean and sun path. But for the sake of this exercise, I'm just going to delete that. And then over here is also the hour of the day that you want to take. So for this one here is quite tricky to be used, because this is not like from which hour to which hour, but from which hour, and it's calculated by many hours. So for example, here is calculated from starting from 1 a.m. and then the count is 24, which means that it's going to take from 1 a.m. to 1 a.m. in the next day. So if you want, for example, the calculation from 9 a.m. to 3 p.m., you need to set this as 9, but in here you don't set it as 3, but you set it as 6. So 9, 10, 11, 12, 13, 14, 15. So that's how you do the calculation in the sun analysis in here. So it's quite tricky to be used, so you need to calculate a little bit, use a little bit of math. So if you want from 8 to 2 p.m., you just need to do that. So that's the hour. So that's the month. That's a day. That's a date, which is very straightforward, and this is a month. So if I change the month, for example, to summer in the US, it will go straight up there. So it's really depending on the EPW file location. If you're doing it in Melbourne, you can download it from you can find a Melbourne one. But for this exercise, I'm just going to keep it as the US. So I'm going to still preview that, because it's going to be useful for the next exercise that I want to show you. So the sun analysis that I want to the sun analysis is actually this one here, this component here. So if you toggle the false into true, it'll calculate the sun. It'll calculate the shadow casted by the buildings. So I need to maybe bake that one first, so my zoom is correct. Yeah, there you go. Preview off. So there you go. So that's a sun analysis in summertime in San Francisco. So as you can see here, the way to read this is that if you see the graph over here, that's sort of like the accumulation of shadows during the day. From the set time over here. So it's from 8 a.m. to 2 p.m. So it's 8 a.m. to 2 p.m. So this is shadow cast. This is how the shadow is casted. So what you want to have a look here is this chart on the right side, which has the what's called the hours. So this means that how much time does an area receive the sunlight during the time that we insert in this hour, day, and month, and hour, day, and month. So as you can see here, there are if you can see in this situation over here, for example, this part over there, so that means that this area only receives 3 hours of sunlight per day, and that area receive only 2 hours sunlight per day, and this little nooks here receive only 1 hour sunlight per day. So that's how you read the sun chart. So this is a really good analysis to allow critical spots that needs more sunlight access. So designers and urban designers and architects can decide which area that needs some sunlight So I want to show you next is to how this can have a high resolution, because as you can see here, it's quite pixelated. It's depending on the grid size over here. So this is the trickiest part, because the grid size means that how big will each pixels, quote unquote pixels, that will generate the analysis such as. So if you make the grid size larger, it's going to calculate even faster, but you will have a lower resolution, because it's sort of like the image. The higher resolution that you want, the smaller the pixel, but it's going to take a bigger file because it has a lot of pixel. So to have it as an extreme, I will show you 20. So 20 looks like it's a pixelated as such, but if you want a really high resolution, you want to go to 1. So it's going to take quite a while to calculate because it has a higher resolution. So it's probably take about 10 seconds. It should take about 10 seconds for this kind of scale. And also, while we're waiting, this grid size actually depends on the unit that you put in your Rhino over here. So for example, I set it as millimeters. So the grid size will take as 1 millimeter. So bear in mind, if you use it for an urban scale, and you put the urban if you model the urban model in millimeters and in real life size, for example 10,000 millimeters, that means that 10 meters, you must take notice, because the grid size will make 1 millimeter instead of 1 meter. And if that's the case, when you try to have a sun analysis in that kind of unit, it's going to take really long time. So bear in mind to use bear in mind to make sure that the units is actually on par with the scale of the model. So if you make a model, it's a really big scale model, just use the meters. So this will be adjusted to 1 meter, and you won't have a problem. So as you can see here, it's already rendered, and it has a very finer and higher resolution. But as you can see, it's quite taking a toll on the computer as well to process this unit, because it's a really high resolution. It's similar to the way Photoshop does with the high resolution image. So I'm just going to change this back to 5. So it's really the only time that I recommend you to use the grid size as the smallest one is when to render it or export it to have like a presentation. But if not, if you just for a work in progress, you just use the lower scale. So I wanted to show you if that's changed. It's going to be a winter analysis during 8 a.m. to 2 p.m. As you can see here, this is a very useful for urban designers and architects alike to create to recognize and to acknowledge dark spots of the cities and crevices. So as you can see here, in winter times, it makes sense that these spots here, they have a very minimum sunlight access during the day. And if you look at the sun, I'm just going to make it this one smaller. Scale. Not enough. That's probably a meter. Meter size. So what do you want? is to that's too small. That's probably 0.005, because what I want to show you is just to see how the sound pass scale really have an information that's connected to this one here. So as you can see here, you can see the shadows casted by the buildings, but then you can see the sun position over there. So it really has a has a connectedness between this diagram over here and the sun analysis over there. Well, it makes sense because in the Grasshopper, this sun analysis depends on the position of the sunlight. But this is a really good tool just to inform the designers in how to maximize the sunlight access during the day. So that's it for today. The next video I will show you how to do a sun subtractor, which is already covered in a part of the sun subtractor strategy is already covered in this video. So I'll see you in the next one.